Hello again. The tour continues now. We're heading into the measurement section of Chapter 2. We're going to be taking a look at various angle and line distance relationships in three-dimensional shapes, as well as some volume and surface area implications around it. So continuing along, look at the micro concepts that we have here. We're down in, we're actually in this section right over here. We've already done the other things in the micro concepts list. So let's continue. We're down here. Yeah, seen that. And here we go. Okay, the first thing we need to be able to do is begin to, draw these shapes with a bit of clarity. There's different styles, that are out there. A common one you'll see is with broken lines that are in the back of an object. This Necker cube one doesn't have broken lines, or it's a little ambiguous. I mean, some people see this as being the front square, but others see this as being the front square. That's not terribly important, but we do need to get into the habit of drawing them well, and I'll show you in class how to do that. There's also some consideration of vocabulary. We can't just say, use colloquial English terms and just assume everybody knows what we're talking about. So now in mathematics, we use the precise mathematical terms. So in these places that people often refer to as corners, they're actually called vertex, the plural of which is vertices. A line where two different faces meet, or two different sides meet, it's called an edge. And of course, face is the appropriate title for what used to be one of the rectangular or any polygonal section that is one of the sides. Okay, so here we go. Other shapes we're going to be looking at are square-based pyramids. You can see there's a base there. This is like the kind you'd find in Egypt, I suppose. One for the triangular base, or referred to as tetrahedrons. Tetrahedra, and then there's a variety of other ones, not just hexagonal but pentagonal and all sorts of them, and we're going to have to get a little bit proficient at drawing them and also referring to the relevant dimensions in them. There's also a vertex of a cone, which is its peak at the apex of its height if it's standing on its base like that. There's also the height. Then there's this side one here which is called the slant height, and for spheres and hemispheres there's really only one measurement that we care about, and that's its radius. Okay, now let's take a look. This is an example from your textbook. They're asking us first off to find the length of the line that connects D to F. Now, if you've got really powerful three-dimensional spatial reasoning, you might be able to tell where that is. Like if you were holding up a cube or a rectangular box, a cuboid, where that line is. Most people, when they're new to this, they struggle a little bit to kind of quote-unquote see it or get it. I'm going to show you some top tips and tricks for how you're going to work this out. Later, after we found the length of that diagonal DF, we're going to then try and find the size of angle BDF, which is therefore from B over to D and then up to F. Now that's that angle in here. But, of course, to calculate that angle, we're going to have to know some lengths of sides. And then we're going to have to apply the right principles, whether from SOHCAHTOA, right angle trigonometry, or possibly from non-right angle trigonometry. I'm not really sure. So how do we begin to do that? What I want you to do is I want you to picture that triangle and its neighbors. So D is obviously a vertex. It's in the bottom corner here. So is B. F is directly above B. And so let's take a look at that triangle. Now, I've animated it, the cube, so we can get a look at that. Now, don't look at the vertices labels. I've mislabeled it. But you can see that triangle in there. And when you apply this animation, it becomes a little easier to visualize. So watch it as it goes around. It's coming around to the same orientation as the one in blue, right about there. And it's going to spin around one more time. So you can see that angle. It's in this red diagram where it's labeled A inappropriately. It should be labeled D to coincide with the one in the upper right. Did I say left or right? Anyway, so what do we do? How do we actually figure that out? Well, I'm going to change the slide now and show you what we do. We look at the three edges that make up the triangle, and we determine whether or not any one of them points perpendicularly at a surface or a face that contains another edge, and it does. Notice that this edge down here is in a plane or a face that's perpendicular. It's almost like the corner, the edge between two walls of a classroom and the floor that we walk on. So if you highlight it there, you can see that we must have a 90-degree angle here, because this line here is perpendicular to the face that is its floor. So any triangle like that would have a 90-degree angle. Okay, So what does that mean? It means the rule of Pythagoras is in play, because it's a 90-degree angle, and SOHCAHTOA trigonometry is in play. So that's all good stuff. Okay, if I'm going to do this kind of stuff, I'm going to have to know some measurements. So first off, this line down here, it happens to sit as the hypotenuse of this triangle, where this is also 90 degrees. But this side over here is going to come into play now. This one's 6 because this one is 6 and they're the same, and so that's why this is labeled with a 6. But this one over here happens to be the hypotenuse of the one that's supported by the legs 4 and 5. So I'm going to put 4 and 5 in here and really put that as root 41. You do not want to go to your calculator and decimalize that. Remember, we had a long-standing conversation about not rounding off prematurely and then reusing those numbers, because in these questions, those numbers will get reused multiple times and in successive layers, and the rounding off will eventually lead to flat-out incorrect answers. You're just getting too far from reality. So we leave it as root 41. Then we can use Pythagoras again on this triangle that's in here. And again, I've written it separately, and I insist that you write it out separately and have a different diagram than the 3D rendering one. And then you have root 77 as its hypotenuse. So now, given that information there, I think that actually answers the first question, root 77. But now I can also go find that angle that they said they want, an angle BDF, labeled with theta on this diagram, and the choice is yours. You can go with a sine relationship or a tangent or even a cosine. It makes no difference, and you get 43.1 degrees. Now, we're going to begin to take a look at some rounding off guidance. Here we go. Here's the section that we need to know right about now. Decimal place accuracy and significant figures. And here we are. Now, I've mentioned this a number of times. In multi-step calculations, you must be careful not to round figures until you have your final answer. Premature rounding leads to an incorrect answer. So you have to leave these things in so-called exact value. I know it doesn't seem like a quote-unquote real number to you sometimes, because it's the first time you've sort of encountered this. And the square root of 77 feels more understandable if you write down that it's like 8 point something, but it's not. It's not acceptable here. And if you go now, this is the cover sheet for an SL exam paper. I'm going to highlight a key feature for you here, which says, unless otherwise stated in the question, all numerical answers should be given exactly, that's what that is, or to 3 significant figures. And that's what that is right there. And we can talk more about that in class and in the subsequent lessons coming up. Basically what it means is this: round off to 3-number accuracy, and allow the 4th number to inform whether or not this one will stand or whether it will be increased. And obviously 3 is smaller, so it stays 43.1. Okay, one more example. Here we got a cuboid. That's just a fancy word for a box whose outer dimensions are 4, 5, and 6, and those lines are mutually perpendicular. You can see that there's a 6 along here, half of which is 3 and 3, there we go, and a 4 and a 5. It says that M and N are the midpoints, so I've drawn the midpoints there and there, halfway between these lengths here, and find angle NEM. NEM. Now, and again, in this triangle, we got to work out whether or not there's a right angle anywhere in it. And just because it might appear like there is, that's not sufficient evidence. You have to have proof that there is. I don't think we can prove that there is, because at no point are any of those 3 edges that make up that triangle pointed perpendicularly at one of the other faces in the shape. So I'm going to go work from the assumption that it's not a right angle. Now, the next thing you do is you try and work out as many distances you can around the shape that might be relevant. If I look at this EM edge right here, I know that this is 4 because it matches this one down below, which matches this one over here. And 3 is half because M is the midpoint between the points D and H. This 5 is the same as this, which is the same as this. Let's put 2 dashes on it. And of course, N is a midpoint, so it is also 3. Now, that doesn't mean we have the lengths of any of the sides or edges of our triangle, but we're on our way toward finding them. Again, we should work out here. Let's see, EM. I'm going to write that down here. If this is E and this is M, This is 4, that's 3, which makes this the square root of 25. Now we can change that to 5 because it is exact. And you can keep doing that. This one over here is the hypotenuse supported by 5 and 3, and that's the squares are 25 and 9, so that makes en root 34. That is exact. Leave it exact. And mn is the same as this line right here below it. That one there is the same as this one here, so I can go ahead and use this triangle down here to find out the squares of 5 and 4 are 25 and 16 respectively, so mn is the square root of 41. What does that all mean to us? Well, I can now imagine that triangle here. I don't know what size of angle this is. I was not really well drawn. I can put m over here and over here. Root 41. En was root 34. And this one was 5. I don't know if that's right angled or not, but I'm not going to assume it is. And if I'm looking for the angle at E, that means I'm going to have to use the cosine rule, which is right here, cosine rule for angles. Substitute the information in like that. This one's across from E over here, so it goes in the lone spot over here on the cosine rule. And sure enough, it's 72 degrees. So it was never a right angle at all, even though it looked like it might be. I'm not really sure, but it's not. Okay, now here's a really long question. I hope you got some popcorn. We're going to get into this one. You've got a rectangular pyramid, and this is the Giza type in Egypt. And it says you've got the base is 8 along this way and 10 along the other way. And the vertical height is 10. Most of those things have been labeled, not all of them. But then they give us a couple other little key things here. It appears that m is the midpoint because they called this equal to 5 as opposed to the 10 on the other side. And O is the point directly below the apex at E, right down there. Okay, so lots of things we're asked to find here. We're asked to find the angle. These are all angle questions between the edge BE, that's this one, and the base of the pyramid. So that's the line right underneath it. So that's what they're talking about there. And well, there's a lot of mess here. Let's just go on and do the first one. So that's the first one we're looking at. And I know that it's a right angle triangle because the line that connects the apex to the spot underneath it is going to be perpendicular to the entire face that includes the line OB. So I can go ahead and take that triangle and extract it. I got this information because I don't have this information right here, so I'm gonna have to go get it somewhere else. It's related to the triangle that's down below here. So I've got the 5 and the 8, which represents these two sides here. That makes this root 89 by the rule of Pythagoras. Why is my pen not working? Oh, here we go. And so therefore this one must just be half of that one over there. And now I then go back to my red triangle and I can see that the height was 10 as drawn here. This one we've really just recently worked out as root 89 over 2. Again, exact value. Don't decimalize this. And that's enough using the relationship of tangent to work out that the angle has to be 64.7 because it's from SOHCAHTOA. Now the next question they said was, can you find the angle between the edges EB here and EC here? Well, you'll notice I put two hash marks in here that are the same because I can tell that this is going to be an isosceles triangle. So what do we do with that? Well, we're going to notice that CEB right here is 180 minus these two thetas here. And since we've already found out previously that angle there was, oh gosh, I forgot to write it down, whatever it was, you have to put that times minus 2 of those in there, and you'll see that those angles must be 50.5. Okay, well that was the one at the top. And now EMO, E to M to O, and again this one here is perpendicular to the floor, so I want to find the angle where the purple theta is labeled there. I already have this 10, so I guess if I could just somehow find this length here, I'd be all good. Well, it turns out that it's half of this one here, which is half of 8, that's 4. So that's 4 as well. And then I can go ahead and use tangent and find out that theta is equal to 68.2. So those are all angles that are retrievable from precise drawing and, monitoring the relationships of side lengths and angles inside three-dimensional shapes. So here we are, exercise 2F. Some nice questions in here. And it's really going to test your spatial reasoning, and I'm going to help you get through it. God, look at that. It's a gorgeous diagram, that one. Okay, so here we are. It's section F, questions 1, 2, and 3. And let's get started, get to work.